Hi Year 12s. I want to say a special shout out to my former students at Lyndhurst Secondary College. Hope you're doing really, really well. Sorry that I'm not there anymore, and I hope that by leaving this video with you, one of the topics that teachers and students are nervous about, which is pseudocode, you will feel more comfortable with it as you work through the content in this video. Pseudocode was introduced in the year 2023 as a new topic in the VCE study design, and there are limited questions to practice on as a result. In this video, I'm going to go through 6 exam-style questions, and if you need more information about pseudocode, the resources that I recommend are the appendix in your textbook and the webpage on the VCAR website. The link is given on the screen at the moment. Let's get underway. So I first want to start by just describing what pseudocode is. It's a way to describe an algorithm or a procedure for performing a calculation. Pseudocode is designed to be read by people, and it's written by people. Until very recently, computers couldn't understand whole sentences like our AI models. Most of the time, in the past, over many decades, computers were only able to do things for humans when we wrote them in a particular language. Such languages include C, Python. You don't need to learn those programming languages. All you need to do is learn to describe a calculation or an algorithm using certain keywords that you will have seen if you've already taken a class in digital technologies or programming. So for example, you might have heard of the keyword if-else for branching or conditional statements. You'll have heard of for and while loops for iteration. And you might have heard of the concept of a function, not in the mathematical sense, but in a programming sense. A function is a program that takes inputs and may produce outputs for you. So things such as Newton's method, the bisection method, and the trapezoidal rule for estimating the area under a curve. These can all be implemented as computer programs, and therefore they can be implemented as functions with parameters. If you have a basic idea of what I've been talking about, then I think this topic is something for you. So if you are someone with programming experience and you are aiming for high marks, then I think you should continue watching this video. However, for the majority of students, my suggestion would be that you should not bother with this topic. And the reason why I'm giving you this suggestion is because there is only 1 mark on exam 2, which is a multiple choice question, in the last 3 exam papers for this subject. And in order to be able to answer these questions, you can't just be learning pseudocode in the last few weeks before the exam. You need about 6 to 12 months of experience reading and writing computer programs, essentially. Or you need to be very comfortable reading pseudocode and translating it into a calculation that you can do on your CAS calculator. I want to say this up front. So maybe the best thing for you to do is to click off this video and worry about the rest of the course first before coming back. But if you are someone who has an interest in programming and you have some experience, then I think you should keep watching. And I'll go through some examples. So I have 6 of them lined up, and I don't know how long it's going to take. It might take a while. Timestamps will be in the video if you want to navigate between the different examples. So the first one comes from sample questions that were given before the very first examination paper in November 2023, when Pseudocode was examined for the first time. Now, if you're unfamiliar with the trapezium rule, I've written it on the screen for you. So essentially, this is a way of estimating the area underneath a curve using trapeziums of equal width, defined by the height of a function. So let's look carefully at what this question has given us. First, it's given us a function, a pseudocode implementation of the trapezium rule. And we are calling it with particular parameters. So we are given the function log x. We are given the lower terminal 1, the upper terminal 3, and the number of trapeziums that this is going to use is 10. However, we're not going to calculate the entire trapezium rule estimate, because we need to read the question very carefully. This question asks for the value of the variable sum, which appears here, after one iteration of the while loop. So we're not asking for the final output of the program. All we need to do is go through the while loop once, which means all we need to do is go from here to here in the pseudocode and find out what the value of this variable sum is. So I'm going to guide you through this. We can actually write down the values of the variables if it helps us. So the function that we are trying to integrate is log x. Our left endpoint is 1, our right endpoint is 3, and the number of trapeziums is 10, although we are only going to consider 1, as will become clear when we work through the program. So what happens in the first line? First, we calculate h. So that is b minus a divided by n. Notice that they've used computer syntax here rather than mathematical notation, because this is pseudocode. Alright, so this is 3 minus 1 over 10, which is 0.2. Next, we store the value f of a plus f of b in the variable sum. So f of a plus f of b is just going to be log of 1 plus log of 3. Next, we define a variable x, which is equal to a plus h. A plus h is the first point inside the endpoints. So this is going to be 1 plus 0.2, which gives me 1.2. I is like a counter. Basically what's going to happen is we're going to let I range from 1 until n minus 1. And since we're only going to go through this loop once, we will only consider the case where I equals 1. And we actually don't need to consider it because it's not relevant to the calculation for sum. So we're only going to execute this line of code once. We've already got this stored in the value for sum. And now we're going to add 2 times f of the value of x which we stored, which was a plus h. So our final value is going to be log of 1 plus log of 3 plus 2 times log of 1.2. Why the number 2? Because it appears in the program. And when you study the trapezium rule, you will learn to recognize that all the values in between the endpoints are counted twice, while the values at the end are counted only once. And then we divide everything by h on 2, so that we are counting trapeziums with width h. However, we aren't interested in the area. We're just interested in this value, sum, because the question asks us for the value of this variable. Okay, so now we just need to go over to our CAS calculator and evaluate log of 1 plus log of 3 plus 2 times log of 1.2. Have your calculator in decimal mode to get the decimal approximation, and it's 1.463, and that gives us option C. So as you can see, once you know what the trapezium rule is, all you need to do is substitute the values given when the function is called into the program. The calculation was actually quite straightforward. You just need a little bit of experience reading some code or pseudocode. If you can read code, you can read pseudocode. Okay, next example. I want to keep this moving. So here's our next question. Here, we are given another function. This one is called the bisection method. The bisection method is studied in Year 11 Maths Methods, and it's a method for finding a root or an x-intercept of a function. If you're not familiar with the details of the bisection method, you may need to look back at your Year 11 textbook. Essentially, it works like this. Let's imagine I've got a continuous function f, and I know the values at a and b. And I know that the value changes sign from one point to another. Because the function is continuous, it has to cross the x-axis somewhere between a and b. So what we will do is we will guess that essentially the x-intercept happens halfway between a and b. And then you repeat. So let's say, for example, that f is negative at the lower value and it's positive in the middle of a and b. Then when I call the function next time, this is going to be my new b, and this is going to be my new guess for the x-intercept. And then you just continue and continue until you're happy. So here, we are given the value sine of x, and we are going to do 2 iterations of the bisection method. So 2 iterations. The function is sine of x. Our lower value, our lower value is going to be 3, and our upper value is going to be 5. Now, when you think about sine, you know that sine has an x-intercept at pi, which is 3.14. So we know there's going to be an x-intercept between 3 and 5. So let's consider what sine looks like. We've got 3, we've got 5. What happens if I evaluate sine at these points? Essentially, your calculator is in radians. So it's positive at 3 and negative at 5. Okay, so now let's work through this this program. This first part is just error checking. So you don't want to run the bisection method if your interval has the same sign at the endpoints. First, we define the midpoint of the two values which we started with. So our midpoint is going to be 4. This is our first iteration of the bisection method. Now, if the function evaluates to 0, we return the midpoint. And we're done. The midpoint of 3 and 5 is 4, so now we need to check, is sine of 4 radians equal to 0? We already know the answer is going to be no. So we will continue. We will not return from this function. We will continue. So we did not meet this condition, so now we go to the next condition. If f of a times f of the midpoint is less than 0, then my upper value becomes the new then my midpoint becomes my new upper value. That makes sense. So now we go back to the CAS. So 3 was A, 4 was the middle value. Notice that the value of sine has changed, sine, S-I-G-N, from 3 to 4. So in iteration number 1, we have A equals 3, B equals 5. In iteration number 2, we will have B defined by this part of the code because the value of the function changed sign from 3 to 4. Okay, so now we'll have 3 and 4. And it actually doesn't matter what happens next because my new midpoint is going to be 3.5. And we just need to check, is sine of 3.5 equal to 0? Well, no, it's not. We already know that because we need pi to get 0. And so when we run through this loop the second time, you'll calculate sine of 3.5, and your next interval will either be 3 to 3.5 or 3.5 to 4. But the value of mid, or the midpoint of the interval, is still going to be 3.5. And so the answer is D. Can I send this to the back? No. So in the second iteration, we have A equals 3 and B equals 4. And then the midpoint that was generated was first of all 4, and then it was 3.5. Okay, next example. This one is based on Newton's method. It's a strategy for finding the x-intercept of a continuous function, which is differentiable. Our approach is to choose an initial guess, which I'll call xi, or x0, it's up to you. Draw a tangent to the graph, and find where that graph intersects the x-axis. The x-intercept of that straight line, which is a tangent, is your new guess for the x-intercept, and you continue repeating this process. So if you wanted to, you could do this, and that will give you your next guess. Now, I'll leave it to you to derive this formula if you haven't seen it already. If you're doing year 12 methods at this time of the year, you probably haven't seen it yet. So you'll come across this soon and you'll derive this formula. Now, in this question, this is as close as we get to writing pseudocode. Essentially, we have a partially completed implementation of Newton's method in pseudocode. And we need to choose from a range of alternatives. So, we are told we're implementing Newton's method with a tolerance of 0.01. What this means is, if my initial guess changes by less than 0.001, then we terminate the algorithm and return whatever guess we have. So you'll see here that there are 1,000 iterations. The reason for that is if we don't have that 1,000 ceiling, this program would run forever and your computer would freeze, essentially, because you wouldn't be able to do anything else. So they've got a line saying next x equals previous x minus f of previous x divided by df of previous x, where df is the derivative and f is the function. So this line here looks a lot like this formula. So now we just need to define the tolerance part. We want xi to change by less than 0.001. Now we need to be careful. Xi can increase or decrease. It's okay for the guess to move to the right instead of the left. So the problem with options A, B, and C is they only consider the change in one direction. So we can rule them out immediately. Options D and E, you will notice, have these lines here. The difference between the next value and the previous value is between negative 0.001 and positive 0.001. That's what we want. So we're only going to consider, well, I'll say we can rule out options A to C. So now we just need to consider options D and E. So when this program is finished, do we want to return the previous value of x or the next value of x? Well, if I start, it's stored in the previous value, and then the program, after each iteration, generates a new guess, which is called next x. Clearly, this is the one that we want to print. So, the answer is option E, because next underscore x is the guess calculated at each iteration. Okay, now we're going to go through 3 past exam questions. So this is the real deal now. As you're looking at this, think about whether you can do these questions in 1.5 minutes. If not, maybe leave pseudocode for another day and focus on all the other content in the course, such as calculus, probability, functions, and algebra. Alright, this is the 2023 exam. This is the very first pseudo question in the course. What's happening here? We have Newton's method executed over 3 iterations for the function x cubed plus 3x minus 3. The derivative, 3x squared plus 3. And an initial guess 1. What we want to do is run Newton's method. So if this looks strange, essentially it's doing this again, except instead of calling the variable xi, they've called it x naught, and instead of saying next and previous, they've just stored it in, they've just updated the same variable. I think it's a bit strange they called it x naught, because usually x naught is reserved for the initial guess. But I digress. Essentially, what we need to do is run this calculation 3 times. So I'll show you how we can do this on the class pad. So what I'm going to do is I'm going to define the function f of x equals x cubed plus 3x minus 3. And then I'm going to define the function g of x equals 3x squared plus 3. The reason why I've defined f and g this way is because now I can reuse the functions. Now, my initial guess is 1. And then what am I going to do? I'm going to take my answer minus f of my answer divided by g of my answer, where g is the derivative of f. So I'm going to execute this once, twice, and 3 times. And what you should see here is by doing the calculation this way, I didn't need to type things in a very tedious, long way. So this can definitely be done in 1.5 minutes, provided that you know how to set up this calculation. I'll copy this into the notes, and the answer is option C. Pretty straightforward if you do the calculation this way, but if you do it manually, it's going to take too long. Alright, next question. Here we are given 2 functions, f of x equals x, and g of x equals cosine of x. And what we're asked to do is to find the x-coordinate of the intersection between these 2 graphs. Now, the way that we're going to do this is we're going to say the difference is between minus 0.01 and positive 0.01. We are going to start at 0.06, and while we are less than the upper bound 0.8, we're going to increment by 0.01 until f of x, so I'll say x equals 0.6, increment by 0.01, that's this line here, until f of x is between minus 0.1 and 0.01. That's going to be our guess for the point of intersection. Not f of x, sorry. Cos x minus x. That's better. Okay. So the return value of this function is x. So by return, it's what is output from the function. So it's only going to return a value when the value of cos x minus x is within this range. So to sort of give you an intuition for this, here is x, well, here is cosine of x minus x evaluated at x equals 0.6. And I get 0.22. Is that value between minus 0.01 and positive 0.01? No. Now, because we're starting at 0.6 and incremented by 0.01, we can immediately rule out option A and B, because these are not valid x values. They need to be between 0.6 and 0.8. Now, option E is something that we could consider. If we went too far too quickly, we might miss this window of tolerance between negative 0.01 and 0.01. So now we need to consider option C and option D. So let's consider 0.72 to start with, just before 0.73. It's too high. This is above 0.01. Now go to 0.73. It's still above 0.01. So only when I reach 0.74 do I get minus 1.5 times 10 to the minus 3. When x equals 0.73, it's too large. So the answer is option D. I think this question isn't too bad, personally. And they gave you a picture. The picture is really helpful. In this question, there was no picture. You had to know what Newton's method was doing. Okay, last question and we're done. This is last year's exam question, 2024, November. We are given a cubic polynomial f of x. We start with an algorithm, and it's going to print some values for us. And the question tells us that this algorithm prints the roots of this polynomial. So just remember, the roots are the values of x, where the function evaluates to 0. So in other words, they are the x-intercepts. Okay. Now this is an interesting question. It's unusual because of the way the program is written. They have defined f, and it just returns, the expression evaluated at that point. So first we have c is f of 0, which is 18. So the program starts at 18. Now, if it's negative, we change the sign. So this line forces c to be positive. It isn't, but for whatever reason, we might want to do that if we chose a different polynomial, f. Okay, now for the loop. While c is positive, what do we do? If f evaluated at that point is 0, print the value. So if c is a root of f, print c. Next, if negative c is a root of f, print negative c. Now, remember, we always start with a positive value. So when we execute this line, c equals c minus 1, we're always going to be starting this while loop with a positive value for C. And based on this part of the program here, it's going to print the positive root first, before the negative root. So now the question is, which roots are going to be printed? Well, as I'm looking at this list here, you'll see that the lists are all the same. It's just that they're in a different order. Now, if it were me during an exam, I would actually check this just so that I knew I was on the right track. So I would solve the equation x cubed minus 2x squared minus 9x plus 18 equals 0. And lo and behold, the roots are -3, +2, and +3. So this function is going to start at 18. It'll try 18 and minus 18, but it'll print nothing. Then 17 and minus 17, 16 and minus 16. It's going to do a whole lot of nothing. Then we're going to get down to 3 here, and then -3 here, and then we're going to decrease by 1, and then it's going to print 2. But when it gets to here, it won't print -2, because based on our calculation, only +2 was a root. And therefore, the answer is D. Alright, so that concludes our tutorial on pseudocode. I will leave it in your hands, students, to decide whether you want to invest time into learning this topic. Remember what I said at the start of this video. If you think that you can solve these questions in 1.5 minutes because you have an interest in or prior experience with computer programming and coding, then I think this topic is right for you. If not, then I suggest you leave it and focus on all other 79 marks of the exam. So remember, pseudocode is a very small part of the exam. Just 1 mark. But if you have questions and you want to have a go at this topic, you are welcome to email me at this address, should you wish to do so. I want to wish you all the very best once again, my students at Lyndhurst. Good luck on your exams. Keep in touch if you wish, and good luck. Bye.